All right, here's the second part of this. I hope we got that part on there. All right, so this is 80 degrees right here. Now watch, I want to kind of show you why these angles are going to be equal to each other. It kind of makes sense, I mean, from what we did earlier. If this is 80 degrees, tell me what angle C is going to be. It's got to be 40. Why? Because the angle is half the intercepted arc, right? Okay, this is 80 degrees. What do you think angle B is going to be? It's going to be 40 degrees as well. Why? Because it's the same arc, right? So you're taking half of the same exact number. So what must be true about angle C and angle B? They got to be equal to each other, okay? Now, of course, they're not always going to be 40, but they're always going to be equal to each other. That's basically what the theorem says. That's not too hard to understand, is it? All right, and you could have figured that out yourself without even seeing the theorem. That's almost like a little mini proof that we did right there, okay? We just kind of showed that that was true, all right? Well, that was kind of fun. Let's do an example, and I'll pause it. All right, I said we were going to do an example, but that example is too easy. It's on page 711, and it's example 2. All right, so if you go to example 2, you can look at it. It's really, really basic, really easy. Let's go to the next theorem. I think that would be a good idea. So what we're going to do, I made reference to this a while back, and I really doubt that you remember, but that's okay. What I'm going to do is draw a diameter. So the diameter has to go through what? The center of the circle. Very good. All right, so there's a diameter. Now watch what I'm going to do. I'm going to draw an angle, all right, and it could be anywhere on here. I want to draw an inscribed angle, okay, that cuts off the intercepted arc is going to be the semicircle. It's going to be 180 degrees, all right. So it's not just going to go from here to anywhere. Where is it going to go? Let's do this in. Let's try this nice blue, all right. So I don't know. Let's just say right here. This is just a random point on the circle. What's it going to do? It's going to cut off a semicircle, and the intercepted arc is going to be a semicircle. So that means I got to go from here to where? Where? To the center? What's a good geometry word for that? It's a chord. It's a line segment. So we're going to go to the what of the line segment? End point. Very good. To the end point. So we're going to go right there. Now this is kind of cool. Watch this. I've never done this on the computer. I always do this by hand on the board, you know, and sometimes my circles aren't that great. A lot of times they weren't that great. But this one actually, this is the first time I've done this. So now watch. I'm going to go from here. Where's the other one going to be? Here, 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 where? Over like this to the other end point. Good. All right. So right there. It's not just a triangle though. Yeah, it is a triangle, but it's not just any triangle. Look at this thing right here. That's a right angle, isn't it? Let me try something here. I'm going to group it together. Now, I don't know. It'd be really cool if I could like just slide it around here. I don't know if I can or not. Watch. It's a right triangle, exactly right. Now, did I just like magically pick the right point for that to happen? No, I didn't. Watch. It's going to be right anyway. I don't think this is going to work, but nah, it's not going to work. Forget that. Let's just ungroup it. I lost. Well, I tried. You know, it's all about trying. Watch this. What if I move this like to right here? Let's get it right on the circle. Right there. And then I'm going to take this.
It's amazing.
Right. Well, it's not amazing yet. Watch this. Then I'm going to move this to right here. So remember I said that it really mattered that I was at that point? Check it out. It still cuts off that semicircle, doesn't it? But look at that angle. What is that angle still? So right angle. So really doesn't matter where I put that. Let's just do it one more time. And let's go way over here like this. Okay, that's right on the circle. Then we're going to take this one and we're going to put that one way on the circle right there. Check it out. What kind of, now it's not exactly, let's see, about right there. That's close enough. So what kind of angle is that? Still a right angle, isn't it? All right. If you look at the theorem says, listen, I'm going to read it, and if you have it open, you should read it along. It says, an inscribed angle of a triangle intercepts a diameter or a semicircle if and only if the angle is a right angle. All right, so it intercepts this. It's an intercept of this semicircle right here if this is a right angle. Or you could say, if this intercepted angle cuts off a semicircle, then it forms a what? A right angle. All right, so that would be a right angle every single time. That really comes in handy from time to time, so just try to remember that. Okay, resume. Okay, now we're going to draw we're actually going to do an example. I've said we're going to do an example twice. Now we're actually going to do one. All right, so let's go back to black on this one. Back to black. Who's the group?
ACDC.
Very good.
It's back in black.
Back in black, right? I think it's back in black. It was close enough. Yeah, not back to black. All right, so here we go, right here. Those are our lines, and watch, they connect this one to this one right here. Let's put some letters in there that they use. They say this is F, and that's G, and this is H, and it's circled J. And this angle right here is 9x minus 3. So 9x minus 3 is this angle. And this angle right here is 4x plus 2. 4x plus 2. So what do you think they're going to ask you to do here?
Solve for x.
They actually ask you to solve for this angle F. But really, it's not that hard once you solve for x. So really, all your work involved is solving for x. Would you agree with that?
Yeah.
So now let's take a look. You know, a lot of times we see stuff like this. What's your automatic response when you see stuff like this? Oh, set them equal to each other, right?
Yeah.
Sometimes that works, or doesn't it? Sometimes it doesn't. Let's see the relationship right here. Now, let's see what we did. What's FH? Give me one word for what FH is. It's a diameter, okay? It's a diameter. Look at, now, everybody listening? Look at GF and look at GH. It's a, what kind of an angle? Now, it's a right angle, but it's according to the circle. In reference to the circle, it's an inscribed angle. Good. It's an inscribed angle. So when I have an inscribed angle and it cuts off a semicircle, which it does, right? Because it goes to the endpoints of that diameter, then this has got to be what? You said it already? It's got to be a right angle. Connor?
Why not? You say that's a right angle when an inscribed angle cuts off a diameter.
Right. Cuts off a semicircle, right.
Does that mean that it just makes a diameter?
Yeah, the only way it can cut off a semicircle if it goes to the endpoints of a diameter, right? Because the diameter is 180 degrees, or a semicircle is 180 degrees. The only way I can get 180 degrees is if I have a diameter going through it. Does that make sense? So you're absolutely right. Now, watch. We got a right triangle. What's the relationship, Alex, between this angle F and this angle H right here? Is that what you're going to answer?
No,
Or you had a question?
I was going to say, so it'd be like taking half of a central angle whose measure was 180. Like that's what the relationship between, you know what I'm saying? Because the diameter
Yes.
is 1.
Yes, exactly right. That's a great point because, look, this arc right here, I should have thought of that, but I'm glad you brought that up. This is 180 degrees right here, isn't it? An inscribed angle is half of its intercepted arc. Would you agree? So, and I usually do that. I don't know why I didn't think of that, but that's good. So watch. This and this right here cut off 180 degrees, so that means the angle has got to be half of the intercepted arc. Well, if this is 180 degrees, what's half 180? It's 90, so that's why it's going to be a right angle. Not just because it looks like it, and that's kind of what I was going with before, and I shouldn't have. We should go by the numbers, right? So would you agree that that does have to be 90 degrees? Not just because I drew it on the cool little program and it looked like a right angle. That's not why. It's because it's half of 180 degrees, all right? I'll give somebody else a chance on this. Tell me the relationship between this angle F and this one H. Monica? Yeah, give me a fancy geometry word.
Supplementary. Complementary.
Which one? Quick. Complementary. Complementary is 90 degrees, okay? So they are. They're complementary, which means, and you're absolutely right, you add them together, 9x minus 3, and you set it equal to 180. Tell you what, we're running at a, not 180. I was just checking to see if you're paying attention. Oh, not really. It'd be 90 degrees, right? Because these are complementary angles, and these angles have to add up to 90 degrees, all right? So let's see, you do your math and you get 7, all right? My college professor, when he didn't want to do all the dirty work right here, he would just do this lightning bolt. He says lightning bolt, and then he gets somebody to tell him what it was, and that's what I'm doing. So x is equal to 7. Okay, you do the math, and x is 7. It's not what they're asking for. They're asking for angle F. So what do? We go 4 times 7 plus 2. So that's 28 plus 2. So what is that? 30 degrees. Check that out. So this has got to be what? 60 degrees. If you wanted to put the 7 in for this, you could, and that would work fine, right? Because 9 7s are 63 minus 3 is 60. That works as well. All right. It is. It's 30, 60, 90. All right. We good with this? Now, we don't know. All right. We'll end right there.